So the Southeast Nevada site is interesting because these near vertical slopes are located very close to the railroad corridor. The area of interest incorporates a 29-kilometer stretch of railway that runs through a canyon system. Our geotechnical asset management approach focuses on two scales, local and regional. The local scale focuses on one slope, in this case a study slope called the Richmond Slide, which is an unstable slope located within the railroad corridor. The regional scale covers approximately 225 square kilometers and includes this railway segment as well as the surrounding slopes and anthropogenic assets. This stretch of railway travels through canyon topography. About 33% of the total railroad track is located within 30 meters of a slope greater than 15 meters in height. An additional 2 to 3% of the track is within a tunnel. There are 5 tunnels total. Thus, over 1/3 of the railway is located near a slope or mountainous terrain and could be in potential landslide risk areas. And we've seen evidence on some of these slopes of either outward movement in the form of quasi-toppling or potentially rotational movement along some slopes. The railroad corridor was built on tertiary volcanic rock. Most slopes are steeply dipping and composed of rhyolite, welded tuff, and welded tuff breccia. The unstable block of the Richmond Slide, which is downslope from the main scarp, has potentially undergone 3 types of movement: rotational slides, rock topples, and rock falls. The cause for concern is that the unstable block, which is dipping and moving into the railroad corridor, will interfere with rail traffic and jeopardize the efficacy and safety of the rail line. And what we're interested in doing is monitoring the deformation or the displacement. An aspect of a geotechnical asset management program is to develop tools to efficiently assess slopes within transportation corridors. One of the primary methods used by transportation agencies is the Rockfall Hazard Rating System, or RHRS, developed by Pearson and the Oregon Department of Transportation in the early 1990s. This system was used to analyze 14 slopes along the railroad corridor in order to investigate the potential hazard and likelihood of future rockfall incidents. RHRS is implemented in 3 basic steps. First, all slopes must be assessed using 10 slope characteristics, ranging from slope geometry to geology to displacement history. Next, these slope characteristic observations are converted to numeric hazard scores. And lastly, these hazard scores are summed to yield the total hazard score for each slope. The RHRS works well for the identification of unstable rock slopes along transportation corridors. Many agencies have adopted RHRS as a performance assessment tool in their transportation or geotechnical asset management programs. Some asset management programs require asset condition updates on an annual basis. A yearly visit by field crews is financially costly and time-consuming. A solution to this problem is to supplement traditional field-based observations with remotely acquired datasets. The traditional field-based RHRS approach is a more robust method relative to some remote sensing techniques, but if an agency is tasked with monitoring a transportation corridor or network, utilizing high-resolution remote sensing imagery may be preferable. A total of 90 radar images between August 20th, 1992 and August 15th, 2010 were processed over the study area in Nevada. 40 images were acquired from the ERS-1 and ERS-2 satellites and 50 images from ENVISAT, all 3 which are from the European Space Agency, which were equipped with C-band SAR antennas operating at 5.331 GHz. All images came from the same descending track, which had a line of sight in the north 86 degrees west azimuth direction and an incidence angle centered at 23 degrees from nadir. Persistent scatter interferometry, or PSI, yields few PS points on the Richmond Slide, probably due to the strict high coherence criteria, vegetation, and slope geometry. The available PS points do show a similar trend to the ground truthing data, however. The unstable block exhibits the most average movement at about 2.5 millimeters per year in the downslope direction. Slight average movement is measurable upslope from the main scarp along the more stable block, but at less than 1 millimeter per year. And the adjacent slopes are basically stable, with the only exception being from locations of observable surface runoff.